we're going to have a look at the energy conversion in a circuit. If you've ever wondered why an electric circuit is called a power cable, today we're going to explain that. So we know that in a circuit, we have a conversion of electrical energy into something else. Electrical energy can be converted into light, into sound, into heat. So when this conversion occurs, we actually know that work needs to be done to move electrons through a resistor. And we now know that there's something called work. And this work is equal to the change in kinetic energy. Now this formula in grade 11 doesn't have much meaning because we don't discuss anything else about work in grade 11. But in grade 12, we will be looking at work as a change in kinetic energy. So just make a little mental note about work. Now, work being the change in kinetic energy, it has a unit, and that unit is joule. So joule is actually something that all of us are exposed to every day. When you eat food, the wrapper at the back will tell you the energy of the food, and it's normally measured in kilojoules. Kilo just meaning 1,000 joules. So work also, because it's energy, is measured in joule. Now when we're talking about power, we're talking about the rate at which electrical energy is going to be converted. So we can say power is the rate of electrical energy conversion. The unit that we use for power is called watt. W-A-T-T, watt. And power, the symbol is P, which is nice and convenient because it also starts with the letter P. So power is measured in watt. And watt can be defined as the amount of energy per second. If power is the rate at which electrical energy is converted, and rate has something to do with time, it makes sense that watt is also known as joule per second. So how much energy does it use per second? In a mathematical equation, if we go and we look at power, we can have a formula that looks like this. Power is equal to the volts times the current. But we also know something about volts from Ohm's law. We know V equals I times R. So if we go and substitute this into V's place, we see that we have another formula for P, which is going to be I times R times I, or we can say I squared R. And similarly, we can get to a third formula, P equals V squared over R. So these three formulae will always be given to you on your formula sheet during tests and exams, but we need to know how to use them because sometimes we only get voltage and current, other times we get current and resistance, and other times we get voltage and resistance. And it depends so that we can figure out what our final set of numbers must be that we use to calculate power. Now in South Africa, our power outlets are normally 220 volts to 240 volts depending, and then if a light bulb is marked as a 60 watt light bulb, it basically means that that light bulb can radiate 60 joules of energy per second in the form of light and heat. So it uses 60 joules per second. If a light bulb has a rating of 100 watt, it can radiate energy of 100 joules per second. So as you can see, a 60 watt light bulb will use less energy than a 100 watt light bulb. So if you go and look at light bulbs at your house, the more the watt measurement of the light bulbs, the higher the energy usage of those light bulbs. So the more energy it uses per second. Is there a difference in the intensity of light between a 60 watt light bulb and a 100 watt light bulb? Of course. If you have 60 joules per second or 100 joules per second, there's more energy per second in a 100 watt light bulb, meaning it will be brighter than a 60 watt light bulb. So you have to decide, are you going to pay more for electricity or are you going to have brighter lights? It's up to you. As long as you're not paying the bill, don't worry about it, right? So how do we now actually go and work with power? And this is what I want to show you quickly. If we have a series circuit and it looks like this. And let's have a resistor over here and another resistor, and we have a parallel circuit. Now you'll see that I'm just doing a very basic setup here. I'm not including much, but we go and look at the effect that a series connection has on power or a parallel connection has on power. Let's make this resistor or light bulb 4 ohm in size, and this one 6 ohm. And let's go and do the same over here. This will be a 4 ohm light bulb and a 6 ohm light bulb. So if I tell you that the 4 ohm and the 6 ohm light bulb have a power source connected to it of 4,8 volts in both cases, when we have volts and resistance, we can go and calculate the current. So if we use Ohm's law, I equals V over R, and we know that over here the voltage will be 4,8 volts. There is negligible resistance from the conducting wires and the battery. So we know that we can use this 4,8 volts as our external voltage, and we divide that by the total resistance in a series circuit. The total resistance in a series circuit will be R1 plus R2. 4 plus 6 gives me 10. So 4,8 divided by 10 gives me 0,48 ampere in terms of current. If I go and I do the same for my parallel circuit, remember that I have parallel resistors here. So to go and calculate parallel resistance, it's going to be 1 over 4 plus 1 over 6, which is going to basically be 3 over 12 plus 2 over 12. That means it's 5 over 12 for 1 over RP. But if I'm interested in RP, it's going to be 12 over 5, which is going to give me 2,4 ohm. Can you see in my parallel circuit, my total resistance is lower than the value of my smallest resistor. 2,4 ohm is lower than 4 ohm. So if we go and calculate current now in the parallel circuit, I equals V over R is going to give me 4,8 over 2,4, and that gives me 2 ampere. So when you look at a series circuit and a parallel circuit, we can see that in a series circuit, the more resistors we have, the higher the resistance. But the current is lower in a series circuit compared to a parallel circuit with the same resistors. So people often think we win when we have a parallel circuit because our overall resistance is lower. Our overall resistance went from 10 ohm to 2,4 ohm just because of a parallel connection, but we're using more than 4 times the amount of current that we do in the series circuit. And remember, current is what we pay for. So the more current you use, the more power you are actually using. Let's go and relate this now to power. Let's go and calculate the power for a 4 ohm light bulb first. For the 4 ohm light bulb, if we go and we take our formula I squared R and we take 0,48 squared times the 4 ohm, it's going to give me a value of 0,92 watt. If I go and I look at the 4 ohm resistor in my parallel circuit, I go and calculate its power. I'm going to use V squared over R. So it's going to be 4,8 squared over 4. This gives me 5,76 watt. So as you can see in the parallel circuit, the power of the 4 ohm light bulb is the greatest, and therefore it will burn the brightest. It's strange. When you have a parallel connection, light bulbs, the same resistance, when we connect them in parallel, the light bulbs that are connected in parallel will have more power, which means that they will actually be brighter. That makes sense because it's using more current. So all of this we can use then to determine our actual cost of using electricity. And that's why it's so important to understand power. We can also go and do the same for the 6 ohm resistor, and without even showing you the calculations, if we go and calculate the power of the 6 ohm resistor in series versus the 6 ohm resistor in parallel, the 6 ohm resistor in parallel will use more power and it will burn brighter than in the series circuit.